Hello and welcome back to my channel. Today we're going to be talking about the rotational volume of things with holes. So this is called the washer method. So we have the washer method. Realistically, what is happening here is we have the space of our graph. And more specifically, there is going to be some separation, some space between the axis of revolution and our actual shape. What this is going to do for us is it's going to leave this hole, it's going to make a donut shape in our disk. In order to account for that, what we're going to do is we're going to take the rotational area, so the volume of this outer piece, and we are going to take out the volume or the area of that inner piece. And this is where we get our big R squared minus little r squared. Big R squared is going to be the outside. The little r squared is going to be the inside. So we're going to follow that top minus bottom a lot here again, but we need to be thinking about the fact that we're rotating it around. So we need to think about it as the outside minus the inside. So the first thing we're going to look at is the volume of a solid that's the result when the region enclosed by the curves is revolved around the x-axis. So we have y equals 2x plus 2, y equals x squared plus 2, and we're revolving it around the x-axis. So the first thing we want to do is just label which equation is which. We have y equals x squared plus 2 because it's that parabola shape, and our other one is y equals 2x plus 2. So we need to decide which one is our big R, which one is our little r. We also need to decide our bounds. So I need my A and B, so our starting x value is on this x-axis. The lowest x value we have is 0. The highest x value is this other point of intersection, which is at 2. So A is going to be 0, B is going to be 2. If we were to rotate this around the x-axis, this piece down here is going to be the inside of our disk. This side over here is going to be the outside of this disk. I can tell because it is the top of our two functions. This one is the one that is higher up from the axis of rotation. It's a little bit easier if you can visualize what this might look like if we rotated it around, but that is a little bit hard for some people, like myself. So I go based off of, are we above or below the axis of rotation, and which function is farther away from that axis of rotation. So big R in this case is going to be that line, this linear equation, and little r is going to be this parabola. So r is 2x plus 2. Little r is x squared plus 2. Okay, now we're going to plug it into our formula. So our volume is equal to the pi times the integral from a to b of big R squared minus little r squared. And this comes from the area of a circle, so pi r squared, but our radius is those two subtracted from each other. So volume is equal to pi times the integral from a to b. A was 0, b was 2, of big R squared minus little r squared. So we're going to have two sets of parentheses. We need 2x plus 2 and 1. So big R squared minus little r squared, which was x squared plus 2 dx. So we have to remember which one's which, because I have subtraction here, so it matters the order that we do stuff in. And we also need to remember the squareds. So I need to remember to take that radius and square it. So if we were to if we had to solve this out by hand, we would need to square both pieces, simplify the equation as much as possible, do our integration like normal, use FDC number 1, plug in those bounds, and simplify. If we use the calculator to do this. One of the things that we might want to do is leave pi out for now and do just this integration in the calculator, so that way we can choose to plug pi in together or not. Everything is just dependent on if we have calculator access or not. If we plug this in to the calculator, it's going to give us 48 over 5. So this is going to be 48 pi over 5. Our revolving, a lot of times, is a setup but don't solve, depending on what's going on. Part of that has to do with what kind of solving it is or what kind of setup. Sometimes they have a setup a problem in two different ways. So the big thing that we look for, then the big difference between washer and disk method, is that space between our axis of revolution and our shape. Okay, so if we look here, we have find the volume of the solid. That results when the region enclosed by the curves is revolved about the given axis. Our axis this time is x equals negative y squared plus 2 and x equals y. Our functions, and our axis of revolution is going to be x equals negative 2. So we have our linear equation, x equals y. We have our parabola, x equals negative y squared plus 2. So looking at this problem, we're going to be revolving around x equals negative 2. We want this in terms of y. We're still going to do big R squared minus little r squared. We just are going to have our equations in terms of y. This also means we need to look at y values instead of x values. So one of the things that I may have to do is solve for those points of intersections. I can do that by setting those equations equal to each other and solving. But we are not going to do that in this case. We have a graph. We're going to use it. So we have a is equal to our y value, that's the lowest where they intersect, happens to be right here, and that happens at y equals negative 2. The y value that is where they intersect at the upper part here is right here, and this happens at 1. So I know my a value is negative 2, my b value is 1. We still want that idea of big R being the equation that is farther away from the axis at any given point. So if I look here, if I go from the axis of revolution and I travel over, I hit that line first, and then I hit the parabola. So big R in this case is going to be that parabola. Negative y squared plus 2. But I also need this to be the distance from the axis of revolution. So just like we would have done from before, our distance here is going to be this distance between our curve and the y-axis, and then also this distance over here. So we are going to use that area between two curves to also subtract our axis of revolution. So we have negative y squared plus 2 minus that axis of revolution of negative 2. We did not have to do it the last time because our axis of revolution was 0, so we would have subtracted 0. So I can go ahead and simplify this to be negative y squared plus 4 instead. Little r is going to be our equation y equals x. We also need to look at it in terms of distance from that axis of revolution. So I have y minus the axis of revolution, negative 2, or y plus 2. So these are the equations that we're going to plug into our volume equation. So I have volume is equal to pi times the integral from a to b, so negative 2 to 1, of big R. Big R is that negative y squared plus 4. It's a radius that we're going to be squaring, and we're going to subtract it from little r. So y plus 2 squared dy. Just like before, if I need to, I would multiply these out. I would then simplify it all together. Then I would integrate it. Then I would use FTC number 1, plug in my bounds, and subtract them from each other, and then I would get down to a single answer, and that answer is going to be pi times 108 over 5. So this volume is 108 pi over 5. Our last one here. Find the volume of the solid that results when the region enclosed by the curves is revolved about the given axis. Our given axis this time is y equals -1. Our two functions are the square root of x plus 1 and x squared. So first thing I'm going to do is just identify which one's which. X squared plus 1 is going to be that parabola, and our square root is that parabola that's kind of on its side. So we have the square root of x plus 1. If we look at the graph, we can kind of see here that they intersect at 0 for x and 1 for x. I know I want to be looking at the x values because we are revolving around this y equals equation, meaning we're revolving this horizontally. So my a value is going to equal 0. My b value is going to equal 1. Okay, big R and little r. No matter which one our equation is, we still need to subtract it from the axis of revolution. So I have the one that if I were to look at it, which is farther away from the axis of revolution, here is the parabola, here is the squared. So the square root is the one that's farther away. So I have the square root of x plus 1, and then we need to subtract that axis of revolution, so minus -1. This gives us the square root of x plus 1 plus another 1, so the square root of x plus 2. Little r is that parabola, so I know I have x squared plus 1 minus our axis of revolution, which gives us x squared plus 1 plus another 1, so once again, x squared plus 2. So that plus 2 is in both. So what we're going to do now is plug it into our formula. So we have the volume is equal to pi times the integral from a to b, which in this case is 0 and 1, of big R, so our square root of x plus 2, squared minus little r, x squared plus 2 squared dx. Once again, if we have to do this by hand, we're going to multiply out those squared. So the square root of x plus 2 times the square root of x plus 2, and x squared plus 2 times x squared plus 2, and then we are going to subtract and simplify those two answers. We then integrate each term like we would do normally, and then apply FTC number 1 to figure out what our total answer would be with the bounds plugged in. If we use a calculator or do that, what we're going to get is pi times 49 over 30, giving us 49 pi over 30. So things that we want to remember with Washer method is we need space between the axis of revolution and what we're doing, and it's any space at all. So if we looked in that third example, none of this is touching the axis of revolution, while in the second example, all of this is space, even though it's attached right at that point. So if there's any space at all, we need to use the Washer method. The only reason we would do disk method is if all of this was touching. So if we were revolving it around, say, that line, y equals x, then we could use the disk method because there's no gap. We need to remember that we're squaring each radius and subtracting the bigger one from the smaller one based off of the distance from that axis of revolution.